So, all right, everyone. So I think I remember last time. But I think I remember last time we did an introduction to how neural networks are supposed to work, right? Specifically talking about, I think, we specifically call feed-forward networks, where you have the general design architecture of a neuron that has weights, biases, and then we're trying to train it, right? And I mentioned that this meeting, we're going to be talking about specifically how we go about implementing this in how we anyway, so today we're going to be going over specifically how we implement neural networks in practice using tensor. Now, I will preface this by saying that I actually don't like to. I am more of a, it's way too dark here, but I'm more of a PyTorch guy myself. I'm more of a PyTorch guy myself. However, the main thing is that TensorFlow is kind of easier for beginners, or we're just entirely unsure of how things work. Did the Zoom meeting end? No. Okay. Good. You hovered over the Zoom thing, and I thought it was over, and I was like, yeah, no, that's what I was. Okay, that's good. No, can you just type the controls so they don't get in the way? Okay. Click on the more, and then there's time. I'm floating the controls. There, thank you. Yeah. So TensorFlow is kind of a pain when it comes to like actually doing this sort of like. I don't want to say higher level because that sounds exclusive or elitist. I mean specifically in terms of doing something that's more like research focused, where like you have to try and like play around with different small parts of the model. So like one of the things we may do is we may be like, oh, okay, we don't want to update, using gradient descent as I mentioned last time. We want to update using another weird folder. Just way of doing that. The library that is used is most often is called PyTorch. And there is the good old healthy tech competition in there because TensorFlow is made by Google, PyTorch is made by Facebook AI. So the whole thing there. But I just prefer PyTorch, but in order to teach you guys how this works, TensorFlow is better. But before we get started with any of that, your standard imports, NumPy, pandas, and matplotlib.
I want to know really.
All right, yeah, cool. So first things first, in order for you guys to get access to this, because I'm sure you guys are wondering, how the heck am I supposed to do this? I'll write this, so I'm going to do this. And you can just take it. I'll just work it or something there. Yeah, but like in terms of like you guys getting access to this, if you look at the Discord pioneers channel, there are two things specifically. One is the link that I sent. Click on the link, open the notebook. You'll notice you can only view the notebook. I do want you guys to be running this along with me. In order to do that, simply make a copy of the notebook by going to actually. I would grab it or the US. Go to File and then like save a copy in Drive and make your own copy that you can play around with. This copy is going to be for us. It's for demonstration purposes. But if you want to follow along, which you will probably do, then make your own copy. Moreover, the other thing I like to make is a giant wall of text with a expand with a file download at the bottom. That is the data we will be using. Hit the download button, and then I will upload it right now. Once I get confirmation from everyone, including the Zoom, that we have. Yeah, just do that tomorrow in the chat, maybe. Yeah. So as long as everyone from Zoom and here just tells me that they've gotten the data downloaded properly. So once you have, just like give me some sort of indication that you did. Cool. Cheers, all three of you. And does everyone in Zoom have it? Everyone in Zoom, do you have the data downloaded or are following along in some way? If so, please say it in chat in some way, shape, or form. Yes. I'll wait for like one more yes. Following. All right, cool. Lovely. So now that everyone has the CSV downloaded, here's what we will be doing. Step one is you want to click on this little file thing right here, right? Then click on upload. Okay, wow, that's already there for me. Click on upload. And then you want to go to wherever you stored that CSV, hit open obviously, and then just it'll upload there, right? Your secret, right? Yeah, that's what I'm saying. And so that way you will have all the data downloaded. Now, if any of you are curious as to what the data we'll be going over is, basically I kind of was looking through Kaggle. I was like, I wonder what data would be useful. I don't know, something as a example. And turns out that FIFA cards are actually really good. So actually, first things first, how many of you guys watch soccer like at all? Football? How many of you are going to yell at me for calling it soccer and not football? That's the second question.
There's some people that listen here.
Yeah. With that said, okay, none of you watch soccer. Okay, that's disappointing. That's very disappointing. But yeah, with that said, if any of you have ever know what EA Sports is, they make a lot of sports video games. I guess in America, the most popular would probably be Madden. I say that like I'm not American, I was born in San Francisco. Like, the most popular probably Madden is the NFL. FIFA is like the equivalent of that for soccer. And they have like a whole thing, which is called Ultimate Team, that has like a bunch of different cards that you can like place players on different teams. So it's like you could put like Cristiano Ronaldo and Messi on the same team, and like it's like people like doing that. I think it's kind of stupid. It's like it's basically not a game, or it's just NFTs for soccer obsessed sports pros. Except you don't spend real money, you spend fake money.
So it's a worth version intention.
Yeah, and also for reference, if any of you guys kind of take the whole idea of like a lot of games nowadays having like loot crates and loot boxes and stuff, yeah, FIFA Ultimate Team was like the first game that actually introduced that, because they would open packs and get new players. So if you hate like loot boxes and stuff like that you have to pay for, this is the game that started it. So good luck with that. Direct your hate to EA, please. But with that said, as a quick quick thing, this is what FIFA cards will look like. And the most important thing about them is that they've got a rating, they've got a position, they show which country the player is from, they show the team that they play for, and a bunch of different statistics for the play. Right? There are also some other more embedded statistics in there. I think like there's a bunch of crap around here. So like and it's supposed to quantify like how good the player is specific. So like for example, let's take the GOAT. Messi has he's like 30 something by now, so obviously his pace or speed is very low. However, he's still really good at shooting, he's great at passing, he's one of the best dribblers in the game, but obviously he's not a defender, so he has no defense. So yeah, that is essentially what these FIFA cards are.
They'll really call Messi right now.
He's boring. He scored 6 goals in 11. I'm mad about it, don't worry. Anyone who is watching the YouTube video, I'm a Barcelona fan, so please don't talk to me about soccer. I'm very angry. Barcelona's absolute trash this year. But with that said, so I'm actually, are you busy?
Not really.
Okay, cool. Then yeah, just cool. So with that said, can you run the first few cells? With that said, what we're going to do is essentially try and predict the prices of these players. So it's similar to how some people actually, do useful things with their time, and we'll predict things like the stock market and, try and like actually get some more money. What we're going to be doing is we're going to be taking a look at the in-game auction house that they have on FIFA Ultimate Team and trying to predict how much in-game currency these cards will sell for, right? So as you can see here, this is our data set. We've got a bunch of different things. So like the names of the players. Like Pele, Ronaldo, these are a bunch of like the really high rated icons, or legends, like historic cards. You've got their rating, you've got the positions they can play, the card type, which is labeled as Virgin here, a bunch of different attributes, which I'll go over briefly. SKI is skills, so like it gives you like a star rating from 0 to 5 of how like skilled the player is. So like 5 stars would be like, your average Brazilian player type of circles around you. Whereas like 0 stars would be like a goalkeeper that can do nothing but weak foot is basically how good their weak foot is. So obviously, people have a left and right foot, and then like some players actually can use their left foot for like actual things, whereas some players are just absolutely useless to get it on their non-dominant foot. So that's what that is. Pace, shooting, passing, dribbling, defense, and physical. Those are all kind of self-explanatory. Popularity, I have no idea where that came from, but I guess it's scored of like how many users play with this card on the thing. This all came from like one website that like aggregates all the data for these cards. So like we'll just kind of go with that score. Club tells you which team they play for. So like in Messi's case with the PSG, unfortunately, it's not Barcelona anymore. For league, it tells you what league that team would be in. Country tells you what their nationality is officially according to FIFA. The reason I say officially according to FIFA and not just where they were born is because according to FIFA, you can change that. So like, I think the famous example is, actually the best is the famous example, he actually lived in Spain for most of his life, to the point where he's like, for all intents and purposes, he's Spanish citizen and stuff, but like he plays for the Argentine national team, he's born in Argentina and all that stuff. Similarly, there are other players, I think there's a guy named Imran who used to play for France, but due to like his grandmother, whatever, and because the French team never started him, he was like, screw it, I'm joining Spain. So he changed like his official nationality according to FIFA and thus registered to play for the Spanish national team. So you'll see like this stuff actually does change very often, very occasionally. But yeah, this lists the country that they play for according to FIFA. AWR and TWR stand for attacking and defensive work rates, respectively. Basically tells you what part of it they're on, or what part of the soccer field they're on. So like for example, like an attacking player would be further towards the front more often, so they have like a high attacking work rate. Whereas like a defensive player would be, towards the back, so they have a lower attacking work rate with a higher defensive work rate. Right? And then you look at the price, and the price is exactly how much they cost at some point in time, according to the transfer, or according to like FIFA's transfer. So all of that said, you guys need to know none of that frankly, but we're gonna go with it. So you can slow down a bit.
Yes.
Okay, all of that said, first things first, we're going to need to clean out a bit of the state. Now, here's all of this, what all of this does. First, we usually have two types of data. You've got categorical and numerical, right? I think I mentioned last time, categorical data is data that has categories, so 0, 1, 2, 3, etc. And numerical data is data that can be on any sort of like real numbers. So if you scroll up just a little bit so that the data frame is new, you can just go last for time. I won't load. Yeah, cool. So, for example, you can see like in the first column, in the position column, right? Positions or like the position they can play is like its own category, right? Because like each player, like there's a set number of positions or a set number of position combinations that are in the game that each player can have. And then like card type is obviously a categorical thing. However, things like your stats like pace and dribbling and all that stuff, that's a numerical value, right? And in general, when you are working with categorical data, you want to be able to assign numbers to it. So simply just going like from a 0, 1, 2, 3, 4, 5, similar to like a Likert scale. You just want to be able to assign numbers to that so that you can use those numbers in your machine learning. And so what we're going to be doing is our first step in terms of cleaning this here is to just assign numbers to it. So this little for loop right here, why do you
I'm just checking the font time.
keep me on my toes? This little for loop right here is just going to take all of the stop moving. This little for loop right here is going to take all of the columns with these headers here, and it's going to just essentially convert them into categorical. Specifically, what it does is it typecasts them into the categorical type according to pandas, and then it converts them to the numbers that are associated with each category, and then turns it back into an integer. That's what that line code means. You don't really know. The reason I didn't do attacking and defensive work rates with this is just because they're both measured by low, medium, and high, and this just kind of goes by like the first one it sees is 0, the second one it sees is 1, so on and so forth. And like I didn't want to take the risk of having like low, medium, and high be different numbers for each of them. Because like when I tried it, there would be cases where like AWR for attacking work rate, you'd have like high would be mapped to like 1, but then like for defensive work rate, high would be mapped to like 2. So that makes 0 sense, in my personal opinion. And so just for the sake of interpretability, I think this manually with the replace then, which I'm assuming someone talked about. Maybe. Yeah. If not, you pass in the dictionary and it basically says, okay, anything that has like the value L replaced with 0, it has M replaced with 1, it has H replaced with 1. Right. So just run that cell blindly. And so I'm going to do it. What's up? Run the cell. And you'll see that if you could look at all of the well, you can see it right here. If you look at like position, they've all been converted to numbers, right? And these numbers are associated exactly with the card type or like whatever, the category that card belongs to. I also dropped the name from the data frame. I kept the names in originally just because it was kind of cool to like see like which players are which, but frankly, we don't need to know the player name in order to do any sort of like analysis or any sort of machine learning with them. So we're just not going to bother. Right. And moreover, another fun thing is like, when you're using machine learning, you want to try and minimize the amount of covariance you have, which means the amount of data that you're using that's dependent on other data that you're using. So like, for example, if I'm trying to measure, if I'm trying to like pinpoint where someone's from, right? Trying to figure out their income and also trying to figure out their parents, or trying to figure out like their income and like what school they go to. Could be kind of covariates because like pretty you kind of go to private schools, things like that, right? Things that like there is some sort of relation. So if I were in some way to use the names, that could actually have some sort of covariate of popularity, because you could imagine like more popular players like Messi and Ronaldo and all are going to be used a lot more than some random dude in the middle of the English fifth league, whatever. So with all that said, now that all of our things are numbers, our next step, so I'm going to be scrolling down all the way to the next cell, is to normalize the data. Normalize the numerical values of set. What normalization does is it makes all of the data like zero centered. For so if you have like numeric data, like the mean of it will be 0 and the variance will be 1. The reasoning is that it makes it sort of more closely fit a standard normal distribution, and thus as a result, it's just much easier to do statistics with it. I understand a lot of that's gibberish. Frankly, there's no easier way to explain it other than just do it. But it essentially makes your data easier to play with. So what we're doing here is we're normalizing all of our numeric columns, and then we're just going to erase them. No, you don't really want to normalize categorical data because it makes no sense. Because like if you take the mean category, like what is that? You know, like when you give it to a model, it kind of makes no sense. Whereas I think categories are 1.5, that makes a lot more sense. So normalizing something like that, it's done. I don't know if it's necessarily most people in the world, but normalizing your numeric data is actually useful. Just like different scales and sort of that's like you want to try and keep all of your data constrained to like one specific scale and not going between like random different scales. It's like one thing can be from 0 to 2000, one thing can be from 0 to 10, so on and so forth. So if you run this cell here, you can see that what we do is we just normalize the data. In terms of specifics, what we do is I make a version of the data frame that doesn't have all the categorical things, and then just normalize it by subtracting the mean and dividing by the standard deviation, and then I just reassemble it by just if it's in the norm, I just take a copy and then like I reset it. And so you can see here that like scales are no longer like some sort of number from 0 to 90. They're just like 3 point whatever, 2 point whatever. And this is just so this would mean that whatever the scales here were like 3 above the like it's like it's like 3.2 compared to what just don't worry too much about the comparison of that. There should be the next cell after this. So this next cell was a product of last minute desperation, but the entire point was notice how previously the price column was the exact price for the player according to the French market in the amount of in-game points that you would spend to acquire the coin. Well, you can do machine learning with a regression problem like that. However, some of the stuff that I did later kind of required that we use categorical problems or categorical data. So instead of doing it like that, all I did is I split them into bins. So you would have like, for the first 999 coins, any player in that range would be like, bin 1, bin 0, any player from 1,000 to 1,999 would be bin 1, so on and so forth. So specifically, you just take the price divided by 1,000, take the floor of it, convert to an integer, that's the bid that you get. And the number of bins that we have obviously is like the maximum bin number that we have, and then just add one to it. So you run the cell, you'll see that if you go to the price column. Why did that not work? Did it not save a change or scroll down? Huh?
Actually, this is a good question for the class. So this is the last cell that we did, right? We normalized it into with variables, we reassembled it, and then we just did a head command to see part of the data set. Now we are getting the following error about the name of the data set. Looking at both of these cells, can anyone explain why this initial assignment is not working? Names removed.
No. That's definitely not it. All right, that's not dismissed together.
No data depth that I can see.
Yep, that's the right answer.
Richard is correct. Basically, what it's saying here with the name error is that it doesn't know what data df is, because if you look up here, our final data set that we ended with is called data df const bin. So this is the name that we should have been using the whole time.
So reason is that your boy made a mistake and forgot to set data here, so don't do that.
That's so sad.
So what you're gonna want to do, and this is how you're gonna make the edit here, is you're just gonna want to go to the top of the thing. And just write data. Yeah, equals. Copy. And when you run the cell, now we're good, right?
Hey Bill, what does the copy command do?
Copies the data frame.
Is it a deep or shallow copy?
Doesn't matter. Right. It's a deep copy. It copies the value. It doesn't copy the reference for those who are curious. And remember what a deep copy is for one variable. But point is, I just copied all the data to another variable. The reason I'm doing that is because again, in case for future, and this is common good practice with notebooks, like as you make edits, like every chunk of edits you make, don't just like keep using the same, like don't just use DF or like this, the same data frame that's like the raw one that you loaded. And after you're cleaning, don't have them be the same name, because then when you start to like go back and like testing which operations of cleaning like broke something, should like the names start getting crossed all over because notebooks save like their last current state and not like per cell. So just in general, try to keep different names as it gets different stages of the process, so that things don't get all crossed. But with all that said, we're not done with our data cleaning. So I'm going to go to the end to the pricing. No, the horizontal. Yeah, if you go to the price, you'll see that it's not like 4.2 million anymore, it's like 4,200, which means it's in bin number 4,200. So 4.2 million to 4.29 or whatever, yeah. Anyway, 4.2 coins. So with that said, after the fun part, we're going to be building a model. So as mentioned, okay, stop moving, get a little trigger happy. So as mentioned earlier, we're going to be using TensorFlow. Standard practice is import TensorFlow as a fuck because STF, bro, because hello. Import TensorFlow as TF, because nobody has the time to sit there and type TensorFlow. But yeah, you'll see that like frankly I did that, but I actually didn't even need to. But with that said, it's just I don't know things, which I think I needed to, but whatever. Anyway, so some of you run that up. It's gonna take a while, that's why I'm saying run it. And also another thing you'll notice, which is another thing I hate on TensorFlow, it takes 38 years to import sometimes. Oh, not this time. No, I know why it didn't. Fork. All right, this will take a bit. So it's not in the GPU runtime. But if you convert it to a GPU runtime, we're gonna lose all of our current progress. But that may make the neural network take 38 years to run.
So converting to GPU runtime makes the neural network longer.
No, shorter, significantly shorter.
Okay, do you want me to?
Okay, yeah, everyone's cool with this. Actually, you know what? I shared it as the runtime. So, oh, never mind.
We're already on you.
All right, never mind. I just got lucky. Google. Yeah, I'm obviously TensorFlow takes forever to import, and on all of the machines that work, it takes forever to import as well. So, no, that's lucky. Excellent. Fun story. One of the projects I'm working on right now, our first thing is everything's written in TensorFlow. We're going to so that we can actually do it. So yeah, this is how we'll do it. But with that said, now that's imported, the next thing is a standard thing. Someone in Samra will go over this more in detail next time. But security by security. I like the way this guy thinks. But what we're specifically going to be doing is we're going to be splitting the data into a training and a test set. Now, someone's someone's probably going, where's your validation set? If you don't know what that means, he'll tell you that.
Where's the validation set, Phil?
It's not something I care about right now. You're not going to find it. But the point is that in order to train your model, obviously you need some data, but in order to verify that the model works, you also need more data that verifies that the model is actually useful in some way. So the data that verifies that your model is good is called like a test set. Or well, specifically what happens is your training set is the data you use to train the model. Validation set is then the data you use to verify your model is good, and then the test set is like the data that you were going to deploy your model on. So if you think about it, then like training set is like again the data you use like for facial recognition. Training set with images you use to train your facial recognition model. Validation set, the images you use to ensure that your facial recognition model can like recognize people properly. And then the test set would be like faces that it sees when it like takes pictures of them. So more or less that's how that works. However, For our purposes, I'm just gonna be playing a little back and loose with conventions, so we're just gonna split the training test. And we're just gonna test it as like a validation set, quote unquote, to like validate the models. Standard practice is in general to not run on the test set more than once. Once you have run on your test set, do not make any edits to the model, because at that point you're like training on the test set, which is not useful in any way. That's not machine learning anymore, that's just like the limit numbers. So that's standard practice. However, again, I'm playing fast for this for the purpose of teaching you guys how tensor works. So we hit the run thing. Also, like another thing is that like usually for like a quick and dirty way to split things up, you can use SK and string and split them to just do it away. Next up, now for the real actual good part of this thing, is building the model itself. So if you remember last time I talked about models as being like a sequence of layers, right? And each layer containing some number of neurons, right? And you try to like, take a bunch of layers and like you take a bunch of layers and you cram them together and shove all the outputs into the other neurons, and then eventually at the end you get your output, right? Now, specifically, what models do and what these machine learning models will do in case of something like a classification problem, like what we have here, is they try to output what we call a probability distribution, right? Now that may be kind of scary, but in reality, what that basically says is, okay, I have like some number of classes here, right? So let's say we have like 5 classes, right? In this case, we have like 8,500, but let's say we have like 5 classes, right? But the thing we'll try to do is it'll output something that's like, what's the probability of being class 1? What's the probability of being class 2? So on and so forth for all different classes, right? Naturally, all of those probabilities will sum up to 1. But what that basically tells you is it's a distribution of what are the chances of being one class or another class or another class or so on and so forth. And basically the prediction that it gives, so when it goes, okay, this thing is from class 5. That's basically saying, okay, which one is the highest probability? And then it picks the one that's the highest probability and says, okay, that's the class that you belong to. So that's essentially what we try to do with the model, right? Is that the output needs to be the number of output neurons, number of numbers that we get at the end, needs to be the needs to be the number of classes that we have. So in our case, the number of bins that we have here. And the input, which we're in the input layer, should be the size of the data that we're showing. So how many numbers are we throwing into the model? So that should be the inputs. Now, in TensorFlow specifically, there are so TensorFlow Keras has a lot of different layer types for more than just even like the fully connected multi-layer percent prime networks that we're doing. However, for the purposes of this level, the first more important one is understanding that, okay, so first thing is you have your input layer, right? This is more or less just a dummy layer that just like makes a number of neurons that you just put the numbers in. So like if I've got a vector of size 10 that I'm feeding into the network, then it will just make 10 neurons, like how's the vectors and pass them on, or how's the numbers and pass them on. And then you have a sequence of what's called dense layers, right? And those dense layers are basically you take a bunch of neurons and then you connect each one of them to all of the neurons of the next layer and so on. So they're called dense because it's like a fully connected or like a densely connected graph is like the mathematical reason, so they call it a dense layer. But all of that reasoning aside, dense layers have again, exploring with TensorFlow, you see that all of these things have like hundreds of different like parameter combinations that you can change. But in general, for when you're defining a model like this, there are 2 main important parts of a dense layer, right? You're going to want to be defining the number of neurons in that layer, and then what kind of activation function you're using. Now, I've gone and defined the activation functions because if I'm being realistic, most machine learning is using the same activation function all the time, which is ReLU, which is a ramp function. So it's like 0 for anything less than or equal to 0, and then it goes up to like y equals x for every positive number. And then at the end, specifically, what we have is something called the softmax. The softmax function is somewhat important, and I'm not going to talk about the actual function because it's kind of involved. If you want to look it up on Wikipedia, you can, but it's kind of involved. But with that said, what it does is that the layer before this, right? Remember from like neural networks last time, it could be like a bunch of different numbers, right? And they could have like a bunch of different their values could be all over the place. What a softmax thing does is it says, okay, well, I'll take all of these things, right? And then like, okay, we'll compute like the weights and the biases, and we'll get like, in this case, we'll get like 8,500 different numbers, right? We need each one of these numbers to be a probability of being in a certain class. And so what the softmax function does is it takes all of these numbers and transforms them in such a way that the output vector ends up being the type of probability distribution that we want. So that's why on the output layer, I always put the softmax function, because that will ensure that you get like probability distribution, which is what you want. Now, for the rest of them, it's entirely up to you how you build this. And so what I'm going to be doing is just kind of leaving it up to you guys. So we have 3 people in person. This actually kind of works. First things first. Does anyone feel like we should add more layers, add less layers? You think that we should leave it as is? I don't know. Take a look. It's cool as is? Yeah. Sure. Cool. Okay. How many neurons do we want to put in the first one? Pick a number. They can be literally as high as you want, by the way. Just like make it less than like 100,000, because at that point it's like 5,000. 5,000. Cool. Cheers. Why is that not? Why is it? People don't like, oh, no, that's not. Cool. Next one. How many neurons do we want? 10,000. 10,000. All right. This is okay. Wow. Oh, went a lot higher than I was expecting. Sure. And last of all, how many neurons do we want? Need a third number. 50. 50. Cheers. Thanks. So, in our extraordinarily theoretical network that we're just going to run with, we've gone and we have a network that now has input layer of size x shaped 1, which means it. So remember that x is your right. So remember that x is like our training data. So it's got all of it's like every single one of those attributes that we listed for each card. And so the shape of it, or the second dimension of it is going to be the number of attributes per example. So we're basically telling us that okay, whatever number of attributes that we have for each example, that's the amount of numbers that are going to be going in at the first one. Network. So there's going to be going, okay, so this is, we'll take the number of numbers you have for each example, for whatever. We then go, okay, so we'll have 5,000 neurons with a regular activation function in your first layer. So it feeds them into those, it feeds all your good old neural network stuff, feeds it into the next layer, which has 10,000 neurons with the regular activation function, does all of that, feeds it down into the third layer, which is 50 neurons with the regular activation function, does all the computations, feeds that then to your last layer, which has 8,500 in our case. So the number of examples we have, or the number of classes that we have, it feeds it into a layer with that many neurons and a softmax activation function. So that then our output vector is the probability of being, is the probability distribution over each class. Yeah. Everyone understand that much? Any questions on that part? Because that's like the most important thing. So let me check the chat here.
I don't think I don't have any.
No, there's nothing in the chat. I'll give it like 2 seconds for anyone to type anything. Cool, cheers. So, with that said, we can then run the cell song.
You didn't run the small already.
I don't remember what I had for breakfast. You can remember running the song. And yeah, so now before I run this next one, first things first, by the way, I define the model building in like its own function just because I wanted to compartmentalize it. But this next question, this next cell is another very important part of the thing, right? So remember how I said originally that we were doing a classification, specifically trying to classify which price category each one of these cards belongs to, right? That means that our problem is a classification problem. I mentioned last time that all of these things are trained via optimizing some sort of loss function. There are set kinds of loss functions for each sort of task. So for example, for Sohab and I, what we're trying to do in our research is predict the rank of a resume, right? That can be any number from 1 to like whatever the heck, it's some sort of like ordered list. And so what we're going to be using is a regression model. So we'd be doing a different class of loss function because we're interested not in trying to map each one of these to like a bin or a category, but we're interested in trying to find a numerical value that describes the rank of a resume. In this case, and that is what we call a regression problem. In this case, a classification problem is trying to figure out which one of these categories each one of these things belongs to. And so you pick a loss function that essentially penalizes you for getting the wrong category. And so the loss function that we're going to be using, which is what the general used loss function is for any sort of classification task, is called categorical cross-hatching. Again, look it up on Wikipedia if you want to see all the details. I can't remember the specifics of it, but it's essentially kind of like take the probability and like take the law it out, like far apart it is and go with that. So the good news is you don't need to worry about all the math and the specifics of it. So what we're going to be doing is we just need to specify when we compile the model what sort of loss we're using, and so we can just give it the string categorical underscore cross-hatching. If you look under technical documentation, they have a multitude of different loss functions that you can use. However, you can look at that on your own. Another thing that's important is metrics. We're going to have a whole section 2 meetings from now, I believe, something like that, yeah, on performance metrics, which essentially tell you how well your model is performing. And it's a little more complicated than you actually may think, but for our sake, we're just going to go with accuracy, because why not? Right? Accuracy is essentially the number. Yeah, everyone knows what accuracy is. We'll go down the test grade. So essentially how correct you are. And then the optimizer, this is going to be on the scope of the class, but it's basically the whole scheme that we use to try and update the weights every time we get something wrong. The optimizer right at the beginning is called Atom Optimizer. It's kind of the one that's used, although most of the time people just use, honestly, of late I've started using mostly what's called just normal SGD or normal stochastic gradient descent. But details, don't worry about all that stuff. Just use what we're using this called because we've got an optimizer. So if you run this cell here, what you'll see is that it will print out an entire description of your model. Not entire description, but it will print out a description of your model. And oh my Christ. Okay, never mind. So you can see here that, as mentioned earlier, we've got our first layer. Usually this summary, by the way, omits your input layer. If you're wondering where that is, don't worry about it. We just don't have input layer. Or we have input layer, just kind of it's kind of don't worry about it because it's kind of the constant. So you can see our first layer, 5,000 neurons, which means that this none is a placeholder. It's like, if I feed in 10 examples, then the next thing's going to have 10 examples. Each of them will have 5,000 neuron values for those 10 examples. But if it give it 100 examples, same sort of deal. So that none is just a placeholder for the linear algebra and the math to do its thing. But in general, you'll have a layer with 5,000 input examples with 5,000 neurons in it. That has a total of 90,000 parameters. Now, you can sort of actually hand calculate that yourself. If you know this input size, so the number of the size of the vector you're feeding into the model, and then you know that each one of these neurons has to have one weight, or it needs to have a weight for each one of the entries in the vector you're feeding it, and it needs to have one minus. So it's going to be 1 plus, I think our input size 16, 17-ish. So 1 plus 17, and then you multiply that by 5,000. And that's going to be the number of, so it's going to be 18 times 5,000, which actually does come out to, comes out to 90K. And so that's going to tell you the number of parameters. But you can hand calculate that, frankly, you don't need to, it's just kind of explain this out to ensure that you understand what you're doing. And so then you can see the next couple of layers. Another fun thing is you can go up to the model definition and you can give each layer a name. I don't remember the parameter name for it, so I'm just don't try to do it. But actually, do you remember? I don't know. You can try layer name or name or something, or whatever. You can give them a fun little name. Usually those are used when you're doing research models, or big models that Google and all will use. They'll have names and all design. That'll be designated which part. So ResNet, which is a big convolutional neural network model that's used to recognize images and stuff. That one will have different layers. Will be convolutional block 5 layer number 3 will tell you that it's in block 5 of the network with it's the third convolutional layer and so on and so on. Let's see, try and actually find it. She's on to the top.
I don't think it's on the top, bro.
It will be. Oh, it's a keyword argument. You're not gonna find it.
Okay, forget about it.
Yeah, well, don't worry about rewriting solve it. But yeah, you can give them names, otherwise by default it just kind of goes this sort of mess. But yeah, at the end, then this is somewhat important, is you can just gloss over the numbers and go, keep going. But I will say, take a second to look at the numbers that it shows you. So at the end, it shows you the number of total parameters, right? In our case, because of the absolute insanity of what these shows, we have 51 million parameters. Now, keep in mind, that is 51 million individual numbers that our computer needs to go continually look through, be like, okay, you got it wrong, and update for every single one of them each time we get something wrong, or for each example to generate. You can imagine it's not very super. This is why, again, these models take lots of compute resources, because you've got 51 million numbers that you need to update each single time that you run something. So, and like, I think being honest, 51 million might be on the smaller end, but it's still a lot larger than you really need for this. But you know what? We're just really good. All right, so 51 million parameters. Cool. Next thing is, okay, cool. Now that we've built this model, we compiled it, we defined the loss function, we defined the optimizer, we defined the metrics that we want to measure. How do we train the thing? Well, first things first, or not first things first, you just use the model.fit command. Now, small little thing is before that, we need to change the way that our labels are organized. So currently, our labels are just like numbers, right? They're just which the bin number for the car. We need to convert that to probability distributions. Because remember, the model outputs a probability distribution. So in order to measure how good that distribution is, we need to give it a comparative distribution comparison. Now you may be wondering, how do I convert a number to a probability distribution, right? That like makes no sense. What it actually does, because what we're doing is a categorical problem, right? So in general, what we have is, okay, we know that this example is in bin number like 30, right? Which then means that the probability of it being in bin 30 is 1, very obviously, certainly in bin 30, and the probability of it being in any other bin is 0. This process of just changing it, and so what we do then is similar to how I mentioned how the distribution will work. So like the first element is the probability of it being class 0, second element probability of it being class 1, so on and so forth. What we do is we then just go, okay, so probability of class 0 is 0, probability of class 1 is 0, probability of class 2 is 0, you go down the line, and everything is 0 except probability of being class 30 is 1. That whole process of changing it from, just number to these, these vectors that have ones where it's the class is called one hot encoding. And so that's for, converting to all that stuff. And so that's what we're doing here in that first one is just converting it, is one hot encoding our labels. And then this model.fit thing is where we actually train. So some important parameters with model.fit. Your first argument is always your x values. So that is the data you're feeding. Second argument is your y value. Jesus Christ. Second value category, or second parameter is your target thing. So that's the correct categories or the labels we have, right? And then you have a bunch of different parameters that you can play. Look for a full list, look at essential documentation, or so I can cover over perhaps it's use output. And you can see a bunch of different things that I can't be bothered to explain mostly. But the important ones are batch size, which you'll see is none So batch size is basically how, because it's kind of insane to go through your entire data set each training cycle. It kind of takes a random samples a bit of your data, kind of tries to go about it by randomly sampling and it's a significant number of times that everything works out. But so the batch size is the number of examples that you process per update. So instead of updating after every single example you get wrong, update after every 64 examples and just see what happened, then just update the weights then. And usually by default it's I think 32 or 64, one of the two numbers. Doesn't matter. Just well, no, it does matter. It's you can, if you think that you don't need to make as many jumps, or if you think that you don't need to you can look at the data in a more coarse fashion than you can make with a very large batch size, then it's not going to look at each individual example and update every single time. It's going to update less times after looking at more data. However, if you want to update, if you want more often weight updates, if you want to improve, if you want the model to change the parameters a lot more often, then that means you decrease the batch size. Then what it's going to do is it's going to look at a smaller number of examples and then start updating. Then you have epochs or epochs. I don't know what the actual pronunciation is, but I say epoch. The number of epochs you train for is the number of training cycles you go with. So you'll to train it, you do a whole pass of your data, and then you after each example or each batch, each number of batches, you go and you update your data, you go and you update the weights, right? That whole process of, looking at a batch, updating weights, looking at batch, updating weights until you get to the end of your data set or your training data set, that's called 1 E, right? The number of epochs you train for is the number of times that you're going to repeat that whole passage over your data set of updates. And so we've done 20. They can be whatever number you want. I've seen papers where for some models, like get things working quite well, they do like 32,000 or something. At some point, it just becomes like a game of how much you want to think. And usually, usually what we do is we just kind of go for how much do we have like overhead for, or how much do we have the ability to, how many epochs can we train for, and just like before like we run out of RAM and stuff like that, and then just let it run. Do what you want. And then for both, it's just standard. It just means do you want it to go gross output or not. Personally, yes, never set it to 0 because I don't know why you'd ever train a model and then not want to look at what the fuck is happening while it's training. So
you just have a lot of faith in the model.
Yeah, if you just got a lot of faith in the model, that like you really sure everything will work fine. Congratulations, your job, I guess. I don't know. But like in general, I've never seen someone like need to set that to 0. So with that said, now that we know how that works, we can just hit the run button and you'll see it start making this really nice progress bars. I will say this should be actually genuinely quick, assuming you're using the GPU runtime. But we're just gonna sit here and you can see that each number, you'll then see that, okay, so each of these, right, it's telling you some number out of like something, right? Each of these is a number of batches that your data set has been chunked out into. So again, it will look at all of these inputs in one batch, update the weights, as I mentioned last time, and then go on to the next batch and keep doing that for each batch. So what it's showing you is how many batches have gone through each point. Then over here, it tries to compute ETA. Don't worry, this one's always wrong. And then at the end, you'll see 2 main metrics. The loss, which is the actual value of the loss function or the average value for that loss function, of the loss function at that epoch. So basically it measures it runs the loss function to measure the amount of loss on a batch. And so it goes through all of the batches, right? And then it does what do you call it? It takes it gets all the loss values for each batch and then takes the average. And so this is the average loss for that one epoch, right? This should ideally keep going down. It gives you an indication of how well your network's trained. Remember how I said that you want to optimize, you want to minimize the loss, right? So you want to ensure that as you're training, the loss keeps going down. When the loss should always keep steadily decreasing, right? And then the accuracy, which you see at the end here, which is one of the metrics that we told you to track, just measure the average accuracy for the model at that epoch. You can see it's kind of stagnated because we had the training for more than a few epochs for this model. It's kind of useless. We'll see why later. But point is that you can see there's like very little improvement being made, and like the loss function is barely improving as well after 20 epochs, which is usually a sign that okay, maybe you didn't need to train for that long. Maybe you shouldn't train for that long, and you can get away with training a lot less. So that's one of those things that as you're training, you can track all that stuff. And again, this might be something that we talk about a lot with performance metrics. Another fun thing, you'll see that if you connect with this callbacks history function or history object thing. Remember that Jupyter will print like the output of whatever function you ran, and so we just ran the model.fit function, which outputs this history object. What this does essentially is keep track of lists of all of the metrics that you told it to track. So it'll give you a list of 20 different values, which is each of 20 different loss values at each epoch. And then you'll get the accuracy, which is 20 different accuracy values at each epoch. You can graph this, and we commonly graph this in practice so we can ensure that our loss is going down and that metrics are going up, things like that. We generally want to track that stuff. So that history object ends up being reported data that we use not over to plot this. But for this thing, we're just gonna not go. So with all that said, now that this model has actually been trained, now comes time to test it. Now there's multiple different ways of testing it, and frankly, the way that we're doing here is just like the quickest way that I could get it to do things, just because it's kind of easier to deal with. So we're just going to be using model.evaluate. All this does, it takes the thing and it just measures the testing loss and the testing accuracy on a specific on your data set, or on your test set, but you did put the test set. Multiple other different ways of doing this. You can write a little scheme for it. For the final project, we're going to be writing a full length function that will run the test set on your code, and we'll essentially test the thing. So, with that said, you guys can then just run the model. You guys can then just run the cell, and it'll show you how the model performed on data that you have. Yeah, as you can see, you know, we got a decently high accuracy of like 92% or whatever, right? However, you can see that loss is kind of weird. Because like again, you want your model to keep minimizing the loss, and by the end it was like 0.42, but your test loss was like 0.6, right? Now, as for why that happens, well, this comes into the whole issue of data imbalance. Now, as mentioned earlier, you might notice that the test loss was a little high. When I tested it was like 0.8, which is much higher than you want. And like commonly may I add that like once that like we consider the model usually done training when the loss is at like 0.004 or something ridiculous like that. So the fact that we even stopped at 0.4 was already kind of a problem. Right? So, well, why was that a thing? It might be kind of keyed in as the thing, but somehow if you run the next cell, and this is also just first thing, this is something you should always do when you're analyzing your data, and it's part of EDA that I think someone will probably talk about a little bit. Is, you know, looking at the distribution of your data and seeing how it's distributed. Where is, what labels do I have the most of? What labels do I have the least of? So on and so forth. So let's do that then. I'm trying to figure out why that test loss was kind of high. Let's do that. As you can see, it's a bit shit. Essentially, we have way too much of like anything of way too much data from bin 0 to bin 1000. Now, first thing, just some real world sense. Remember, we're talking about beacon cards. This kind of makes sense because, like, most of the cards in the game, I mean, most players would not be highly sought after, and you would not want to pay a lot of money for them. Because, like, again, for every Lionel Messi that you have, you're going to have like 38 other guys at like the English 10th league that like can barely kick a ball around before they fall over. You know, like people that like aren't really worth, aren't really like cards that people want to buy in the game, right?
What? Well, what did the English 10th league ever do to you?
They're English.
You're English.
I'm Britain. I'm not British. No, I'm Indian.
Yeah, well, English, you committed it.
Yes, anyway, English is hard language. But in general, you know, most of the cards on the game, just by definition, are not going to be like high value cards that people are looking at, right? However, that presents a bit of an issue, right? If you give the data, if like think of, for example, if you give like a baby something like this, right, where a lot of everything is towards the first bank, right? Or if you have it, and then you have them, and then you test them on like the same way. They're going to write class 0 every single time because they have like a 90% chance of being correct, right? Now, that presents a problem for us then, because we're unable, we need to actually be good for all of these things, right? We can't just be good in this category, we need to be good for every single category. And how do you fix that? How do we make sure? How do we make it so that our training set is balanced? There's multiple ways. And the methods are called over and understand. We're not going to talk about that, frankly. Except right now. But I'm not going to go into specifics. Essentially, what it does is oversampling is you get more data. Well, sorry, so there's 3 ways. One is you just go back and get more data. Like whatever your data collection method is, you go and get more data. In this case, it's entirely unrealistic because of the data we have, right? We can't get any more. You can't add more cards in the game. You put it off. It's literally later. Like literally the next section, next cell. Good. Okay, scroll up. Right. So then you need to get more data, right? In this case, again, we can't like, you know, put more cards in the game and like whatever. That's useless, right? And that's unfeasible. And in a lot of applications that will be unfeasible. So, like, for example, if you're trying to get something that diagnoses whether or not someone's heart disease, right? You know, I mean, you can't just go around and just get more people with heart disease somewhere and there's like bullshit at McDonald's or something. So it's just trying to get more data points. not gonna happen. So there's ways of fixing. First one's called understand, where essentially what you do is you go, okay, well, how much data do we have? We've got, okay, 12,000 of this one thing, and then like, I actually looked at the numbers, like 7 for like the rest. Okay, sure, let's like cut it so that, way everything's like sort of balanced, everything's sort of like equal, right? Well, in our case, we can't do that, but in other cases, we have a lot of data for like everything, and you just have it.
No, why can't we undersample them?
I'm literally kidding. Oh, okay. Oh my god, thank you. Great, I got right wrong. My sibling. But in general, if you have like say like if you're in a situation where say you have like 5,000 in class 1, but you have like 100,000 in class 2, right? Well, you can still like cut it down, so that's 5,000 to 5,000, right? Or you can even cut it to like 10,000 to 5,000, right? And that's still like a decent size thing that you can train on, and then you just test with your test set and just kind of hope with the rest of the data and then what happens, right? You can do things like that. That's what undersampling is, where you just reduce the amount of data. Oversampling is where you increase the amount of data you have. Now, and so the method that we use with undersampling that I talked about was called random undersampling, where you just kind of like cut data, right? Now oversampling, there's 2 main methods. One is called random oversampling, right? You just take a bunch of these things, right? You already have the examples, you just re-enter them into the data set. So that way you artificially increase the amount of certain data sets that you have just by basically putting the same data back in over and 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 over. Right? Now, can anyone see any problem with doing that? No problems? Okay, well, here's a big problem. Cause we're doing models get overfit, right? And what I mean by overfit is it'll cause your model to then just be like, okay, I need to see this specific example only to get this category. I need to see this specific example only to get this category. It won't think that generally like, okay, people from this category will have like these sorts of attributes. It'll be like, okay, if they're not exactly like this dude, they're not assigned that. That's a bit of a problem, right? Because we're trying to get like general ideas. We want something, it shouldn't be like, okay, well, if someone's 8.5 million, that they must be like, Pele in this case, right? They must be like the Clark or Pele. Well, no, you could also be a Clark or like another really highly rated legend or like another really highly rated card that's out there. You want this to be extensive. So we don't want something like that. We don't want to just randomly increase our data to such high levels, because at that point you start to get things extraordinarily overfit. Right? And so there's a third thing, or there's another thing, which is called, it's essentially pulling data out of thin air, or generating new examples through some fancy mathematics and fancy like methods of interpolation, of just like pulling data out from just random or just distribution and doing it that way. One of the methods that's extraordinarily popular that someone keeps going for is called SMOTE. SMOTE stands for Synthetic Minority Oversampling Technique. Never said these abbreviations were good. Yes, they make technique into letters. But yeah, SMOTE is the method that I've seen is pretty commonly used. I use it, and it works decently well.
Use it.
What?
You use it.
No, we don't. We should. So another fun thing, SMOTE works very well on categorical data, and the reason why I made this thing in the end a categorical problem instead of a numerical problem, or a classification problem instead of a regression problem. In terms of regression equivalents for SMOTE, very, very, very hard to find, very, very, very not well researched. So that's a whole fun game. But all of that aside, we have SMOTE, and we can use it for the categorical data we have, right? So let me scroll down. If you're interested, you can read the paper on SMOTE, you can just look it up. But there's a library that implements it. It's called IMP Learn or InLearn, which stands for Balance Learning. We can install it quickly, just so that you have it. I don't know if the notebook comes equipped with this, we'll just install it. And then it just kind of works like, and I'm not going to give too specific here. If you go to here, you set like the kind of oversampling you do. So in our case, we're using we just doing oversampling and using you can change that to SMOTE, literally change it to SMOTE.
Oh,
yeah.
Why do you put random rules?
I forgot.
No.
It's capitalized. No, it's all caps, right?
I hate caps lock.
You hit caps lock in the space, yeah, nice. Right, so you can use smoke, right? And if you look at inlands like whole thing, there's a lot of different sampling strategies you can use. But when it defaults here, and what we're going to be using is not majority, which means, okay, we know that the majority of examples are from this category. Everything else just keep oversampling, right? And so I'm going to take this out from here. And so now what we're going to do is we're going to run smoke. That was not exactly what I wanted to happen.
Sounds like you're missing a parameter.
Sounds like I am, but also don't actually need that parameter. I don't know why it's getting that. That's awkward. Sure. Oh, that's why I use random mark over sample. Yeah, that's actually why I use random.
Yeah, so one thing we did that.
Because I couldn't figure out the issue. So yeah, smoke, for those who are curious, and that's why this error is happening. Smoke specifically works by using a nearest neighbors. It kind of like plots the data, right? And then it goes by like finding like the nearest data points that it kind of just samples and goes, okay, cool. Well, this is gonna be close, so we're just gonna grab something that looks like this and throw it in there. We're not gonna deal with all of that because trying to hack out all the bugs is not something I have the time or patience or anything for. So if you just run smoke on this if you run, we're gonna just run this random oversample, which as I said earlier, can cause things to be very overfit. And we might find that it does, but with that said, we're running the random oversample. And now what I want to do, and what I forgot to do, which is why it's part of the slide, is just we need to plot the we're going to plot the distribution, the distribution of our training set after resampling. So I'm just going to do this quickly. You guys don't really need to do this, honestly, as far as like I care, like just writing this is fine, but I can pretty much show you guys. Yeah, that should do it. Right. So as you can see, that's still not entirely what I wanted. Oh, that's not what I wanted to go.
It is an improvement.
It is an improvement, but it's not ideal. This was another thing that was getting annoying. Was trying to get things to match up right because we have a lot of different classes. So this gets to be fun. Can't spell. It's just so good. Yeah,
Better.
we can see it's a little better, right? Now, in reality, like it ain't great, but and like there are ways of doing it so that you can imagine like another way I could go about doing this is okay, just like take like what do you do?
Oh, there were notifications.
Oh, okay, fair. But another thing that you could do is you could then just be like, okay, you take like this in and like that stuff. And so the issue here specifically is that like the histogram itself is already cutting things into bits, right? Just to make things easier to look at. In reality, like nothing's like actually like balanced like this way. We've got a lot of cards that are probably with that. I think I looked at within like 0 to 10,000 range. So like it's extraordinarily highly weighted that way. Can you hit the what the hell? But like in general, like this thing's kind of confused. So like 8,500 different classes. And it's trying to be like, okay, well, the majority are gonna have like this many things, and then like it's trying to like match them all there, but that's not gonna work really. So you're just gonna have to humor that, and like this one's kind of like not a great example, but I'm trying to make it work. But in general, you should see that now after we use this, and then if we build the model again, or rebuild and rerun the model, so scroll down a bit and go to and run the thing. We should be able to see, then let's refit it. Oh my Jesus Christ, another brand. Makes sense.
Did we actually use too much rate?
Yeah, we did.
That's really funny.
Okay, yeah, so I'm gonna leave that as an exercise for you. You can run it, you can see how it performs. Ideally, the loss can decrease a little bit. I don't think it's gonna decrease too much, but it should decrease a little bit. You should see somewhere associated increase in the accuracy score. You may be wondering what happened. Why did I run? Well, remember, each one of these for the model, each one of these is a number, right? Now, you may remember computers take a maximum of like 8 bytes to store a number. It's like, what was there, 8 bytes, right? Yes, it takes like 8 bytes to store a number from, if you ever run that, right? If not, congrats, it takes 8 bytes to store a number. Well, if it takes 8 bytes to store a number, and I have 51 million numbers, I then have 400, a little under 480, or a little over 408 million bytes of information. That's a lot of memory. And the amount of memory that Google allocates, because remember you're running on Google's servers, it's Google's GPU server thing, so it only allocates so much because everybody else needs to use that space as well. Yeah, we overshot the amount of RAM that it had. We just allocated too much. We tried to allocate too much. We hit it with like, hey dude, can you spare like an extra like 8 or so? Actually, out of curiosity, how much is 408 million bytes? It should be 4 gigabytes, right?
For a second, I thought you would log onto your computer so that you could use your Epic gaming computer resources.
Yeah, as if I can do that. Okay, so it's 408 megabytes. So we hit it for a request for basically half a gigabyte, and it went no. So yeah, I think by default these things don't have much RAM on them, and like it's probably about a gigabyte now if I think about it. Like, we already used half a gigabyte just loading things. We also used enough to like load the data, each of steps, and then we just kind of went, no, it just couldn't do it anymore. So you can't store all that data. Which is another reason as to why when you're working with tensor code, machine learning stuff in general, make sure you are very conscious of the amount of resources you have. So for example, you might wonder, like for example, if any of you are into graphics cards and stuff like that, you might be wondering about like, when GPUs record, we have 8 gigabytes of VRAM on the graphics card, right? Why is that any useful? Well, that's like the amount of data that you load, right? Every time you run a weight update for each batch, you load the data from all of the data from that batch onto your graphics card, run it on the graphics card, and then it rolls it back to you on your RAM, right? If you have more than 8 gigabytes of data that you're storing on your graphics card in each batch, you're going to break, your graphics card is just going to be like, no, and then the model will stop training because, okay, I don't have the space for this. I don't know what you're trying to do, right? Similarly, in this case, since we're storing everything on CPU, or we're storing everything in our RAM, every time it tries to load the data, it's like, okay, cool. Let's load the data, let's load all these parameters. Now we ran out of RAM. We have no place to store this data. We have no place to store all of the model. We're going to have to just quit. And, in this case, it's runtime. In general, when you are trying to train your model, make sure, honestly, that you start small and start scaling it up as you start to realize that things can run. Because if you shoot for the moon and then think like, okay, cool, like I'm good with like this many parameters, like we did, where we went, okay, cool, 5,000, 10,000, 50, sure, okay, we'll go with that. That can end up making you run out of resources, and then you're just gonna have a hard time trying to, get even one model right. When oftentimes you train multiple models and it's not just again. So with all of that said, I'm sorry to leave on this weird cliffhanger, but frankly, nothing I can do about it at this point, and I'm not going to go back and change the model and retrain everything. But with all that said, that will be this week's meeting. Next time, Silver and Summer are going to be going over an actual example of a project you guys are going to be doing, and yeah, I'll see you guys then. Again, remember.